So number 1 gives us the first, second, third derivatives of a polynomial and what they want of a function. And first is they want us to find the linearization of f. So if you remember, linearization would be the same thing as finding this equation of the tangent line. So we need to find the slope and a point. Well, since we're given the derivative, we know that this is our slope. So we need a point. And we're also given that f of 0 equals to -1. So that means when x is 0, y is -1. So writing it in point slope form, I get y plus 1 equals 2 parentheses x minus 1. Solving for x, and I get my linearization. Part B asks us to write a quadratic approximation for f. Well, a quadratic approximation looks ax squared plus bx plus c, where a, b, and c are constant. So if you take the first derivative, you get 2ax plus b. If you take the second derivative, you get 2a. So what we're going to do is we're going to look at our second derivative. So when x is 0, our second derivative is -3. So we're going to go ahead and substitute that into our equation and solve for a. So a is -3/2. So now we're going to look at our first derivative. So our first derivative, a was -3/2, x is 0, and the first derivative is 2. So solving, we get b equals to 2. So now my original equation, I'm going to have when x is 0, y is -1. So wherever I see an x, I'm going to substitute 0. Wherever I see a y, I'm going to substitute -1. And remember that we found a to be -3/2, b was 2. So solving for c, I get c equals to -1. And if I substitute those into my equation, I get a quadratic approximation. Part C wants us to find the third degree Taylor approximation. So the third degree Taylor approximation is f of 0 plus f prime of 0 times x plus the second derivative x squared over 2 factorial plus the third derivative x cubed plus 3 factorial. So we're given all the information we need. We just need to substitute everything in. So there's my third degree Taylor's approximation. So part D asks us to approximate 0.7 using the Taylor approximation. So substituting wherever I see an x of 0.7 and then using my calculator to find what this is. This turns out to be -0.06. For example 2, we want to find the coefficient of x to the third for the Taylor series. So what we're going to do, since we're trying to find the coefficient of x to the third, we're going to find the third degree Taylor series. So we're going to take the derivative 3 times. So f of x equals 3x. So the derivative is going to be 3e to the 3x. The second derivative is going to be 9e to the 3x. And the third derivative is 27e to the 3x. So if we substitute 0, we get 1. So the first derivative we get 3. The second derivative we're going to get 9. And the third derivative we're going to get 27. So if we write the Taylor series that's centered at 0, we get this polynomial. So we're looking for the coefficient. So the coefficient is 27 over 3 factorial. So as we simplify that, we get 9/2. For number 3, we're given that the Maclaurin series for 1 over 1 minus x is the summation from n equals to 1 to infinity of x and n. And we need to find the power series of x squared over 1 minus x. Well, since we're given this information, we need to use it. So I need to rewrite x squared over 1 minus x as 1 over 1 minus x. So the first thing I'm going to do is I'm going to factor out the x squared. So I can have the 1 over 1 minus, kind of make it a geometric series. And I'm going to have that x squared. So now the 1 over 1 minus x squared looks similar to the one for the Mulholland series. So I'm just going to go ahead and substitute that into my power series. But instead of x, I'm going to have x squared. So I have a power to a power, so I'm going to go ahead and multiply. So I'm going to have x to the 2n. So now I have this x squared in the front. What I'm going to do is I'm going to put that next to the xn. It's multiplication, so I can rewrite this as x to the 2n over x squared. And that's the same thing as x to the 2n plus 2, because same base, we're just adding the exponent. So as we substitute n, when n equals to 0, I get, it should be when x equals to 0, I get 2. When n equals to 1, I get x to the 4. When n equals to 2, I should get x to the 6. And when n equals to 3, I get x to the 8, and so on. So it becomes 2, 4, 6, 8, 10. For number 4, we're trying to find the value of dx dt. So we know that dy dx is dy dt over dx dt. So the first thing that we're going to do is we're going to find what dy dt is. So taking the derivative, so we're going to divide by x. So we get 10 to the negative x to the negative 1. So taking the derivative, we get dy dx is equal to negative 10. Remember, we're going to subtract 1. So we get negative 10 over x squared. We're also given that x is equal to 2. So we're going to go ahead and substitute that for x. And we get that dy dx is negative 5 halves. So we're going to go ahead and substitute that into the equation. We also know that dy dt is 3. And we're trying to find dx dt. So we're going to go ahead and cross multiply. Divide by negative 5. So we get dx dt is negative 6 over 5. For number 5, we're trying to find dy dx if we're given equations in parametric. So we're going to use the formula dy dx is dy dt over dx dt. So we need to find dy dt and dx dt. So since x is equal to t squared minus 1, dx dt is going to be 2x. And since y is equal to 2 e to the t, the derivative is just going to be 2 e to the t. So substituting those into my equation, I get 2 e to the t over 2t. The 2's cancel, and I'm left with e to the t over t. For number 6, we're trying to find a third-degree Taylor polynomial centered at x equals to 2. So since it's a third degree, we're going to find the third derivative. So since f of x equals to ln of 3 minus x, the first derivative is going to be 1 over 3 minus x times the derivative of the inside, which is negative 1. The second derivative, so let me go ahead and write this as negative 3 minus x to the negative 1. Going to be a negative times a negative is a positive, subtract 1. So you have 3 minus x to the negative 2 times negative 1. And the third derivative is going to be 2, 3 minus x to the negative 3 times the derivative of the inside. So now since it's centered at x equals 2, we're going to go ahead and substitute that into x. So ln of 1 is 0. The first derivative is negative 1. The second derivative is also negative 1, and the third derivative is going to be negative 2. So writing that in my Taylor series, I'm going to have 0 plus negative 1 x minus 2, because remember it's centered at 2, plus negative 1 x minus 2 squared over 2 factorial, plus negative 2 x minus 2 cubes over 3 factorial. For number 8, they want us to find the sum. So notice that it almost looks like a geometric series, so we're going to try to simplify this. So I can write 2 to the n plus 1 as 2 to the n times 2. And then I can factor out the 2 because that's a constant, and I can get 2 to the n over 3 to the n. And now I have a geometric series. And because r is less than 1, I know that it's going to converge. So if you remember, the sum of a geometric series is going to be 1 over 1 minus x. But we need to be careful because that's usually when n equals to 0. Okay, when n starts at 1, my series looks a little bit different because the first term is not 1. The first term is actually 2/3. So when it starts at 1, my geometric series is a sub 1 over 1 minus r. So you kind of have to remember. So the easiest thing is to always remember it's going to be your first term over 1 minus your ratio. So always think of your first term. So when n equals 0, your first term is usually always 1 because anything to the 0 power is 1. So if we use our formula for the sum, we get 2/3 over 1 minus 2/3, which is 2/3 over 1/3. And as we simplify, we get the sum of 4. For number 9, we want the series expansion of sine of t over t. So if you remember the Maclaurin series for sine of t, it's sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus 7 x to the 7 factorial, and so on. So what I'm going to do is I'm going to factor out the 1 over t, and I'm just going to write the series expansion for sine of t. And by doing so, I can now factor in or distribute the 1 over t into each of the terms, and I get my new series. Okay, so number 11, we're going to find the interval of convergence, so we're going to use the ratio test to find the interval convergence. So remember, in the ratio test, it's always the nth plus 1 divided by the nth term. And since we're dividing and we have a fraction, we're going to multiply by the reciprocal. So if we simplify, putting our n's together, our x's together, and our numbers together, what we can do is we get n plus 1 to the nth, x to the first, and 1/2. Now, since x and 1/2 does not depend on n, we can move them to the front. And notice that the limit as n goes to infinity of n plus 1 over n is equal to 1. So we're just left with the absolute value of x minus 2. Now, since this is a ratio series, it only converges when it's less than 1. So we have to put, since it's absolute value, between negative 1 and 1. So my ratio converges is between negative 2 and 2. So now I have to check my endpoints to see if my endpoints converges. So when x equals negative 2, if I substitute that into my series and do a little bit of algebra to simplify, notice that the two n's are going to cancel, and we're left with n to the x, negative 1 to the n. This is an alternating series, but this is going to diverge because the nth term is not equal to 0. So when n is equal to 2, we end up with the same thing with just n, so it's going to diverge. So my interval of convergence is just going to be from negative 2 to 2, and negative 2 and 2 is not going to be included. Now the second part of this says, show that the first 9 terms of the series are sufficient to approximate. So what we do is we need to find the 10th term. And the reason we need to find the 10th term is because since we're trying to approximate the 9th term, we need to show that the next term, which is the 10th term, is going to be less than 0.01. So the 10th term, so when n equals to 10, and remember that x is equal to negative 1, so I'm going to go ahead and substitute that, we get 0.0097. So this means that we only need the 9th term to approximate this series with an error of less than 0.01.